This is actually a composite image of a suspected solar flyby that's going past a protoplanetary disk, and the name of the star is ZCMA. And this image is actually composed of these four images from Subaru VLA and the ALMA telescope. And one thing you can note is this long tail of gas and dust that's been pulled out of that protoplanetary disk. And these researchers have proposed that a similar flyby could have happened to our solar system early in its formation, and they've published a couple studies. Trajectory of the stellar flyby that shaped the outer solar system, and irregular moons possibly injected from the outer solar system by a stellar flyby. I'm going to show you one of their videos, and things happen pretty quick, especially at the beginning, so watch closely. The Intruder star is coming right through, and you can see it's spreading out all these objects that were originally going around our sun. Let's watch it again. And looking at late in this scenario, you can see a significant amount of material has been thrown out from the sun, and some has also been captured by the Intruder star. The reason they did this study is to try to explain the origin of the Trans-Neptunian Objects. This is an image from a study done in 1995. This darker line here is the orbit of Neptune. And then you can see this little dashed line in dark red, and that's the orbit of Pluto. And all these dark reddish-brown lines are objects that are orbiting outside the orbit of Neptune. And for lack of a better description, most of these objects can be described as muddy snowballs. Of course, they're relatively large, but compared to the planets, they're very small. These dashed green lines represent objects that are called centaurs, and these are kind of special because they're similar to these muddy snowball objects, but they orbit in the opposite direction around the sun. And interestingly, these centaurs that have this retrograde motion, they actually tend to have more stable orbits than these other objects that are going in the same direction as the planets. And one of the biggest mysteries of our solar system is how these objects came to have these orbits around the sun. So to date, about 3,000 of these Trans-Neptunian objects have been discovered and characterized, at least enough to know kind of what they look like, what their albedos are, and what their general color is, as well as their orbit around the sun. On top of that, there's this cluster of Trans-Neptunian objects, which includes Sedna, but also these other large objects that are orbiting very, very far out from the sun. These are actually going out up to 900 astronomical units, so 900 times the distance of the Earth. And it's a big question, how did they get here, and how do they have these stable orbits that they don't get thrown off from? One solution that's been proposed basically since about 2014 is that there is another planet way outside the orbit of Neptune that's actually orbiting out here, and it's stabilizing the orbits of this main cluster. The problem, though, is that about 78% of its possible orbit has been observed, has been tracked with telescopes, and no evidence of that planet has been found. And what these researchers have proposed is that early in our solar system's evolution, while it was still a protoplanetary disk, a stellar flyby occurred. Basically, a star of similar size flew past our sun at a very specific angle and captured a whole bunch of material and caused a whole bunch of other material to be flung off. So now let's look at another part of their video. So you can see some of the material remains bound to the sun and some becomes unbound from it. And just looking at the bound material now, these are the objects that are like Sedna. In the purple there, you have the ring that's close to Neptune. They are calling the Centaurs the retrogrades, and you can see the inner solar system in teal. So basically, they ran thousands of simulations in order to find something that would work, and they found that that perturber star had to come in at a parabolic orbit, which is actually quite unusual. On most stellar approaches, it's actually hyperbolic, so they wing away from each other instead of going around each other. But from their model, they were able to explain two very important things. First, the Trans-Neptunian objects that have high eccentricity, which means they orbit very far out from the sun. They were also able to explain the ones that were highly inclined from the sun, and also the ones that went opposite of the rest of the planets. So what are the chances this happened? Well, let's read part of their paper. Close encounters are most frequent during the first 10 million years of a star's life, when it's still part of its birth cluster. Simulations find that typically 8 to 15% of all solar-type stars experience an encounter, reducing the unperturbed area to 30 to 50 astronomical units. And that's important because Neptune, which is basically the last planet in our solar system, is 30 astronomical units away from the sun. Even in low-density clusters, you would expect 1% of solar-type stars to experience such an encounter. And in 10% of those cases, you'd expect the star that was flying by to be 6/10 of the size of the sun to about the sun's size, and to approach 90 to 130 astronomical units away. So what that means is you'd have about a 1.5% chance of that happening with our sun. Another thing they did to test their results was they grabbed their expectation of how eccentric the orbits of these Trans-Neptunian objects would be, and they compared them with how distantly they orbit the sun. Now in the black here, the black dots represent the observed Trans-Neptunian objects, and then the rest of these are what's predicted by their model. And you can see at least what's been observed is kind of similar to what their models predict. And another interesting about their model is it makes a prediction of what the size of the protoplanetary disk that surrounded our sun originally was. So based on how far out these objects are found and how much they're inclined, we can get an idea of the size of the sun's original disk. So based on their model and what data we have, we can say that the sun's original protoplanetary disk was at least 150 astronomical units across. Now, a standard size for what we've observed of protoplanetary disks, this would be the minimum, and then 300 would be about the maximum. So what do these researchers have to say? What does this study have to say about this distant planet out in the Kuiper Belt? Well, first of all, this is the Vera Rubin Observatory, and this particular telescope has been under construction, and it's supposed to come online within the next year. So first, everyone's hoping that enough data can be derived from our outer solar system using this telescope that we'll be either able to identify that planet that's out there, or basically get enough data to prove that it's not out there. If that planet can be observed, then the question is resolved. But otherwise, it's going to be high inclination Trans-Neptunian objects that could decide her. If more distant, highly inclined objects are found, they're going to provide a challenge for that.